Welcome to this explainer. I'm absolutely thrilled to take you on a journey today. We're going to bridge the microscopic behavior of atoms with the massive real-world engineering feats that literally hold our modern civilization together. We're talking about something that happens silently, continuously, and powerfully all around us. All right, let's dive right in. So, what could possibly connect a rusting underground gas pipeline, the gleaming chrome bumper of a vintage car, and the battery powering the smartphone in your pocket right now? I know it sounds like a riddle, right? But the answer actually lies in an invisible, microscopic war. It's this relentless, nonstop battle over electrons, and it dictates whether material is going to crumble to dust or literally power the future. Act 1. The players and the rules. To really understand this war, we need to zoom way in. Down at the atomic level, elements are locked in this perpetual struggle for electrical dominance. There are distinct players here, and there are absolute rules. Now, what's super interesting here is this concept of ionization tendency. Think of metals as having highly distinct personalities. Some metals are incredibly generous, They are just desperate to give away their outer electrons and oxidize, turning into positive ions. But others, well, they're kind of stingy and greedy. They hold tightly onto their electrons and totally refuse to change their pure metallic state. This chemical desire to lose electrons, that is the fundamental driving force of our microscopic war. You can essentially think of this hierarchy of personalities as the universe's leaderboard for metals, also known as the activity series. Up at the top, we've got highly reactive base metals like lithium, potassium, and sodium. These elements are so absolutely desperate to shed electrons that they will literally explode when they touch water. Crazy, right? Then, as we move down the list, we pass metals like iron and zinc that slowly rust, until we hit a very specific dividing line, and that line is hydrogen. Hydrogen basically acts as the referee here. Below it, we find the noble, unyielding metals like copper, silver, and right at the very bottom, gold. Gold is incredibly chemically stubborn. It straight up refuses to give up its electrons, which is exactly why a gold coin dug up from an ancient shipwreck still stays perfectly shiny after thousands of years. Lithium's twist, hydration energy. So let's look a bit closer at the absolute top of that leaderboard. Lithium. There is actually a massive plot twist regarding its position as the reigning champion here. See, if we were just looking at pure vacuum physics, just a single atom floating out in empty space, lithium actually isn't the easiest element to strip an electron from. In a vacuum, heavier elements like potassium or cesium actually lose their electrons way more easily, simply because their outer electrons are further away from the pull of the nucleus. But as we know, real-world chemistry doesn't usually happen in a perfect vacuum. It happens in the messy, chaotic reality of water, in aqueous solutions. And let me tell you, in water, lithium absolutely dominates the competition. The whole secret to this lies in lithium's ultimate weapon, hydration energy. Because a lithium ion is incredibly tiny, it packs an immensely high charge density. When it finally sheds that electron and enters the water, it pulls the surrounding water molecules in with incredible, almost violent force. This entire process releases massive amounts of heat. That's the hydration energy, and it completely overpowers the initial energy it took to remove the electron in the first place. It's basically a thermodynamic loophole, and that loophole is exactly what makes lithium the ultimate electron giver in real-world watery conditions. Act 2. Keeping score. All right, so we've been talking a lot about the qualitative feelings of atoms, right? Who wants to give or take electrons? But let's be real. Engineers can't build pipelines and next-gen batteries based on feelings. We need hard thermodynamic laws. Scientists really needed a way to translate this abstract chemical desire into a strict, measurable numerical score. So we move from the qualitative idea of ionization tendency to the highly quantitative standard reduction potential. This is a strict measurement of an element's thermodynamic tendency to gain electrons. And the coolest part, it's measured in a unit we use every single day, volts. But here's the catch. Voltage is always just a difference in potential. And to measure a difference, you obviously need a starting point. Enter the standard hydrogen electrode, or SHE for short. By international agreement, the reaction of hydrogen gas and hydrogen ions on a platinum electrode under standard conditions is defined as exactly 0.00 volts. It's basically the universe's absolute zero-point baseline. Every single other element out there is measured in comparison to this one referee. To truly understand why these voltages actually matter to us, we have to talk about Gibbs free energy. This is the ultimate thermodynamic measure of spontaneity. It basically tells us whether the universe demands that a certain reaction happen entirely on its own, without any outside help or energy being pushed into the system. If Gibbs free energy is negative, the reaction is spontaneous. That means it is going to happen whether you like it or not. And there's this incredibly elegant formula that ties the whole thing together. Delta G equals negative Z Fe. I mean, it is just mathematically beautiful. The E is the voltage we just talked about. F is Faraday's constant, which represents the charge of the electrons, and Z is just the number of electrons moving around. This simple little equation perfectly translates a voltage reading from an everyday multimeter directly into the natural energy flow of the entire universe. It proves that the higher a substance's reduction potential is, the more the universe naturally forces it to steal electrons from something else. Act 3, rigging the game. Okay, now for the best part. Because once you actually know the rules of the game, you can totally rig it. We're going to see exactly how engineers manipulate this invisible microscopic war to build and protect our modern world. Let's look at a literal multi-billion-dollar problem: rust. Iron has a voltage of negative 0.45 volts, which means it's fairly reactive and it naturally just wants to rust. But look at zinc over at negative 0.76 volts, or magnesium way down at negative 2.37 volts. They have a much stronger desire to lose their electrons. So engineers use these clever things called sacrificial anodes. By literally attaching chunks of zinc or magnesium directly to massive iron ships or miles of underground pipelines, they completely rig the thermodynamic game. When the corrosive environment attacks, the zinc or magnesium eagerly steps right up, sacrificing its own electrons to protect the iron. That base metal intentionally dies and rusts away so the vital iron structure can live on indefinitely. It's brilliant. But hey, what if we want to go straight up against the universe's natural flow? Well, that brings us to electroplating. This process brilliantly illustrates what happens when we force the microscopic war to run backwards. By applying raw external electrical power, just pumping energy into the system, we can completely overcome those thermodynamic limits. We can literally force elements that naturally want to dissolve to instead stack up neatly, atom by perfectly placed atom. This is exactly how we coat cheap plastics with pure copper for your computer circuit boards, or cover a standard steel bumper in highly protective gleaming chrome. We are artificially hitting reverse on the natural electron flow. Silver restoration magic. Now, we don't just use this science on massive industrial scales. You can actually manipulate this exact same microscopic war right in your own kitchen. If you have some old tarnished silver, which is just dark silver sulfide, you really don't need to scrub away the metal to clean it. You just need some hot water and baking soda to act as a conductive electrolyte path. Throw in some standard aluminum foil and just drop your silver in so the two metals touch. Aluminum sits way down at negative 1.66 volts, meaning it desperately wants to lose its electrons. Silver, on the other hand, sits way up at positive 0.80 volts. Because of this massive voltage gap, the aluminum effortlessly sacrifices its own electrons, sending them zooming through the solution straight into the silver, forcing those tarnished silver ions to reduce back into beautiful, pure, shiny silver. It's literally elegant thermodynamics masquerading as a messy kitchen trick. Secret of next-gen batteries. So, from the kitchen sink, let's look ahead to the future. Without a doubt, the most critical application of this science today is powering the global electric vehicle revolution and stabilizing our massive green energy grids. Now, what's so absolutely fascinating about this number, negative 3.04 volts, is that it represents lithium's massive reduction potential. Remember the plot twist from the start of this explainer? Because lithium has the strongest desire of almost any stable element to shed an electron, pairing it with a material that strongly wants to gain electrons creates a huge voltage gap. And that massive gap translates to extreme power packed into a tiny, lightweight package. It's what makes lithium the undisputed king of high-energy modern batteries. But, of course, there's always a catch, right? Lithium is scarce, and it's expensive to mine. So engineers are currently looking just one step down that leaderboard to sodium. Sodium-ion batteries operate at negative 2.71 volts. Sure, they offer slightly less pure power than lithium-ion, but sodium is incredibly abundant and dirt cheap. By trading just a tiny bit of sheer voltage power for incredible global abundance, scientists are actively designing the sustainable next-generation batteries that are going to back up our entire planetary grid. Which leaves us with this final thought to ponder. Everything we've talked about today, from preventing massive iron pipelines from rusting away, to making your tarnished jewelry shine again, all the way to the massive batteries that will power a carbon-free world, it all relies entirely on who wins and loses this invisible, microscopic war over electrons. So, how will our continued mastery of this nanoscale electron movement shape our macro-scale, sustainable future? It's a totally fascinating question, and honestly, the answer is going to define the entire next century of human progress. Thanks so much for joining me for this explainer today, and always keep questioning the invisible forces around you.